بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. And I would like to welcome you guys to the final experiment in this course, the temperature control. We left this experiment at the end of the semester because it is the most difficult one to operate. When we say to operate, we mean by that to start up and maintain, okay, and also to shut down the process. Okay, the main objective of this experiment is to operate the RT578 trainer in manual and automatic modes to control hot water outlet temperature of the heat exchanger H1 by manipulating cooling water flow rate through the exchanger using the pneumatic control valve as an actuator. And if we have enough time, inshallah, we will review the second objective, which is identifying the possible disturbances that might affect the control variable and examine the automatic control response under normal and abnormal operating conditions. And when we mean by that, we actually refer to the conditions where if you are running the experiment or the process in a steady state and either a disturbance has been introduced to the process or an equipment failure which might cause the measured value to deviate from the set point. Now, under these circumstances, the automatic controller will, based on the error, will respond to that change, and as a result of that, there will be a change in the controller output signal. Okay, I will leave the theoretical part of this experiment or the introduction part for you guys to read. We have to jump right away to the process description. The theoretical part has been already covered in a previous video, and that's why we will begin first with the process description, guys. Okay, now in this experiment, guys, as you can see, we have two loops. Okay, the first one is indicated in red color, and this is the hot water circuit. Okay, and the other one is the cooling water circuit. Okay, this is the location of exchanger H1 where we have the hot water flowing through the exchanger, and there is also the cooling water flowing in order to absorb the excess heat that the hot water might possess. Okay, now the control variable, actually, guys, as we are going to see inshallah right now, is the hot water outlet temperature. Okay, so it will be much better if we understand or if we describe the process from here. So at the beginning, what we have in here is this hot water circuit, in which as I said before, the hot water outlet temperature from this exchanger H1 will be controlled by manipulating the cooling water flow rate through the exchanger using the pneumatic control valve. Now for the hot water circuit, guys, and before I start talking about the description of the hot water circuits, I would like to inform you that due to the lack of time, I will skip the startup procedure of this experiment because it takes a while to do that. Now what we have in here is that before we start up the experiment, guys, we have to pressurize this hot water circuit with water. Okay, before we started up this experiment, there was almost no pressure in this section or this circuit, and it was partially filled with air. So the procedure involved the removal or pressurizing the hot water circuit with water first, and allowing the air to be vented outside through valve number 16. Okay, now once the system has been pressurized, we need to have the water circulation process in place inside the hot water circuit. That's why we have a small pump right here, pump 2, and this is the pump right here, guys. This pump can be adjusted to be running at 3 different speeds, and for the sake of having better control of the temperature, it has been recommended that the pump should be set at the minimum speed. As you can see, that the knob is pointing at number 1. Number 1 withdraws the least current, okay, 0.14 ampere, and the least current means the least pump speed and the least flow rate. Okay guys, so this pump, after air has been removed and vented from the system, the pump was started, and we have to make sure that the operating pressure during the experiment should not exceed 3 bars. Okay, during the startup, if you have a look at the experimental procedure, it says that the initial pressure of water inside the circuit must be around 2 to 2.2 bars. Okay, and the air, as I said, can be vented through this venting valve or this breathing valve. Okay, now in order to increase water temperature in the hot water circuit, we have an electric heater that is an on-off heater. The experimental procedure, after the system has been pressurized and the second pump was started up, the heater was switched on in order to increase water temperature required for the experiment. Okay, now this is the electric heater right here, and you can see that most of the equipment and the piping system are insulated. It's covered with an insulating material. Number 1, for the safety of the operator of the system, in order not to be directly exposed to the hot pipeline or hot piping and hot equipment. And the second thing is trying to minimize heat losses from the water as it flows inside the pipeline. Okay, now once we start up, or once we turn on the switch, or turn the switch on, guys, we expect water temperature to increase, and that might lead to an issue that we have, which is basically that as water temperature increases, the water inside the piping system and the equipment will try to expand. Okay, and this is a very well-known phenomenon known as the thermal expansion. Okay, the more heat you supply water inside the piping system, the more it tends to expand, and that causes the pressure inside the circuit to increase. Okay, now in order to protect the equipment in the hot water circuit against overpressure or exceeding the maximum pressure, number 1 is we have what is known as the safety relief valve right here, and as you can see, this is the valve number 17, and this valve is designed to open when the pressure reaches 3 bars. Okay, but before allowing the safety relief valve or the pressure safety valve to open, we have what is known as the expansion tank right here, B3. Okay, so you can see that this is valve 4, and then we have B3. And here, guys, you can see that this is valve 4, and we have the expansion tank B3. This tank is used, guys, as you can see here from the drawing. It has some kind of liquid water filled in, or half of it is filled with water while the rest is filled with air. This kind of tanks is used to allow the liquid to expand freely inside the system before the safety relief valve opens. Okay, so that is basically the main function or the purpose of using the expansion tank, is to allow the hot water to expand as a result of the temperature increment inside the hot water circuit. Okay, so the electric heater is now switched on, and the system is mostly running at steady state. what happens right now, guys, is that the pump circulates the water through the side glass, okay, here, and then through valve number 15, and then the hot water flows through the heat exchanger H1. Okay, what we have here is a thermometer that is used as a local direct measuring device to measure the temperature, and this thermometer right here, known as TI3, measures the hot water inlet temperature to the exchanger H1. Okay. Now, as the water flows inside the exchanger, it will, or some of the heat or thermal energy will be transferred to the cooling water on the other side of the heat exchanger. I'm going to come to the cooling water circuit right now. And after that, the hot water will leave the exchanger at a lower temperature. Now this outlet temperature is our control variable, and we have two types of measuring devices used to measure hot water outlet temperature. The first one is the local direct measuring device, and it is a thermometer, as you can see right now, and the other one is a thermocouple. Inshallah, you'll study that in the theory side, how thermocouples are designed and what are the advantages of using the thermocouples for temperature measurements. Okay, now right now the measured value by the thermocouple, guys, is transmitted as an electric signal to the controller. Okay, and the controller compares the measured value with the set point, and based on the error, it will calculate how much is the output signal. This output signal will be sent to the final control element, which is the pneumatic control valve. Okay. Now, and that's it for the hot water circuit, guys. Okay, so the water flows out of the heat exchanger back through the electric heater. It gains, or the temperature increases in the heater. The pump, this small pump right here, pumps the water again, and it flows through the exchanger back again. Now, on the other side, guys, what we have here is the collecting tank B1. This is the cooling water circuit. Okay, we have the collecting tank B1, from which water is being pumped using the centrifugal pump P1. Okay, and the cooling water flows through valve 6, which is the automatic control valve. Okay, then the water flows through the piping system, and then it goes to the heat exchanger H1. The cooling water will absorb the excess heat from the hot water, and as a result of that, you'll see that the outlet temperature of the cooling water, indicated by the thermometer TI5. TI5 is located right here, okay, as you can see. And after that, water flows through valve 8, and then through valve 9, and then back again to the tank through valve 11. Okay, so again, water flows, cooling water from the pump, okay, through the control valve, and then through this section of the piping system, okay, and then it goes through this pipe, okay, to the inlets of the cooling water inlet side of the heat exchanger, and then after that it leaves after it has been heated up by the hot water, okay, because the cooling water will absorb the heat. The temperature will be measured, and then after that the cooling water will return back again through valve 11 to the tank. Now, one important thing here to discuss, guys, is that the cooling water circuit, as it absorbs heat from the hot water circuit, the cooling water needs to return back again to the heat exchanger at the same inlet temperature, which means that the cooling water inside the tank needs to be cooled. Okay, we need to have some sort of cooling for the cooling water before it goes back again to the heat exchanger, because if there is no cooling inside the tank, as we are going to see inshallah right now, the cooling water temperature will continue to increase, and that will cause a failure in controlling the temperature. Okay, so what we have in here, guys, is that for the cooling system, or for the cooling water that we have in here, the cooling water returning to the tank is actually cooled using cold water that is supplied from valve 1. Okay, we have a coil inside the tank through which the cold water flows inside the tank to absorb as much heat as possible, and then the cold water returns back again to the drain. Okay, so this is actually the cooling water supply to the tank. Okay, and as you can see, it flows through valve number 1. Okay, and we have coil inside the tank to absorb as much heat as possible, and then the cold water returns back again through this hose to the drain system. Okay, now one of the things that we don't have here, guys, and I suppose that they are actually very important, is that we don't have any kind of thermometers that is designed to measure the cooling water inlet temperature to the tank, to the heat exchanger. Okay, but what we can assume here, guys, is that since we have a thermometer here in the tank, as you can see, okay, you can see the temperature is a little bit high, and since the pumping process will almost result in no change in the discharge temperature of water, we will say that, or we will assume that the cooling water inlet temperature to the tank is indicated by this thermometer right here. Okay, but in reality, guys, we know that this is not true, because as you can see, the piping section here is not insulated. That means that the ambient temperature, okay, or air temperature inside the lab will affect the cooling water inlet temperature to the exchanger. Okay, as the water flows inside this piping system, some of the heat will be released through the piping system to the atmosphere, guys, and that will lead to a minor drop in cooling water inlet temperature to the heat exchanger. Okay. The other thing that we don't have here, guys, is that as we have discussed in the first video, is that one of the most process variables that needs to be monitored during the experiment is both the hot water flow rate and the cooling water flow rates. Okay, now we have the magnetic flow meter to measure cooling water flow rates inside the circuit, and as you can see right now, it indicates a value of around 77 to 80. But unfortunately, we don't have a flow measuring instrument to measure hot water flow rate in the hot water circuit. Okay, now that's it actually for the temperature control. And in the first video, guys, we have seen that the number of disturbances or potential disturbances that might affect the controlled variable are so numerous here. Okay, I've counted around 15 potential disturbances, or 14, okay, including hot water flow rate. This is the controlled variable, by the way, and the variables that might affect the controlled variable are, as an example, the hot water flow rate, the hot water inlet temperature, the operating pressure inside the hot water circuit, the cooling water inlet temperature, the cooling water outlet temperature, the cooling water flow rates, the discharge pressure of the pump, okay, the suction pressure of the pump, which might be resulting from a change in liquid level inside this tank, okay, and the cooling water, the cold water supply flow, and the cold water supply temperature, and there are also many other things, guys. Okay, so all of these are potential variables that might affect the controlled variable, and as a result of that, it was expected that the startup procedure and maintaining the controlled variable at the desired set point will take much longer time compared to the previous experiments. Okay, now in order to conduct our experiment, guys, what or before we conduct the experiment, I would like to remind you that the thermocouple we have is designed to measure between 0 Celsius and 200 degrees Celsius. And as we have done before in the previous experiments, in order to compare the reading of the thermocouple in Celsius, which needs to be converted from percentage or process value percentage, the reading of the thermocouple will be compared with the thermometer next to it to make sure that both of them are so accurate. One more thing to discuss here, and it is very important, is that unlike all the previous experiments where the control direction was inverse, in this experiment the control direction is said to be direct. Okay, what does that mean? It means, guys, that the error caused by a disturbance in the process is directly proportional to the controller output signal. Okay, so we remember that, guys, before the midterm, that if any disturbance has been introduced to the process, we need first to understand how this disturbance will affect the control variable and what will be the resulting error due to that disturbance. Okay, the error could be either positive or negative. Okay, positive means that the process value is above the set point, and negative error means that the process value is below the set point. Okay, now in all the three experiments that we did before, the control direction was inverse, meaning that if the resulting error is positive, the output signal will decrease, and vice versa. Okay, now in this experiment, if the error is positive, the output signal will increase. Okay, and if the error is negative, this means that the output signal will decrease. So you can see that there is a direct relationship between the error and the controller output signal, or OP in percentage. As an example here, so one of the disturbances that we might have is that the hot water flow rate was suddenly increased. Okay, that can be done by increasing the speed of pump 2. Okay, now if hot water flow rate is increased, then we expect as a result of that the hot water outlet temperature will increase. Okay, it will increase above the set point. This means that we will have a positive error. Okay, and we will notice that when we have a positive error, the output signal will increase, and that is very normal, guys, because as we have seen, if the temperature increases above the set point, we have to bring it back again to the original set point, and that can be done only by increasing cooling water flow rate, which is done by opening the valve, the automatic control valve, more. And opening the control valve means that we have to increase the output signal. Okay, so I'd like you to focus on this point, guys, because most likely you will have some questions in the final exam where you will have to explain how the outputs or the controller output signal will change in case if we have a sudden disturbance or equipment failure in or during the operation of this experiment. Okay. Okay, let's go back again, guys, and as you can see right now, the system is still running. Okay, what we are going to do right now is that by looking at the observation table, okay, considering only the automatic mode, okay, the set points that we have in the manual are 30, 25 and 20%, but the problem that we have here, guys, is that if we have the highest set point 30%, this means that the cooling water flow rate requirements will be very low, and it is very likely that the magnetic flow meter will show 0 flow rates. Okay, that's why I had to change set points to 25, 20 and 15%. Okay, so now let's have a look at the values right now, guys. The first value is the first value in the column is the process value. The system has been running in the automatic mode for a while, so as you can see right now that the automatic controller is actually struggling here. It is trying to keep the temperature at the desired set point of 25%, and it is actually very difficult. That's why it's almost impossible to conduct this experiment in 1 hour, guys. It will be impossible to do that. Okay, so we have the process value in here that can be recorded. So as an example, let's assume that the process is now stable and the process value is showing 25%. Okay, so we're going to write that. It's 25. The controller output signal, as you can see, is around 37.6. So let's write 38% as an example. Okay. The hot water inlet temperature is indicated by this thermometer right here, or temperature gauge. Okay, TI3, which is located right here just before the exchanger, and it reads around 52 degrees Celsius. Okay, so it reads around 52 degrees Celsius. The hot water outlet temperature reported by the TI1 is around 50. Okay, it's not actually 50, but it is around 50. Okay, the cold water inlet temperature indicated by TI4. TI4 is located right here on the tank, and as you can see right now, it shows around 36. Okay, let's get closer, guys. Actually, it looks like 5 and 6, 38. Okay, which is a little bit difficult to read the temperature from there. And the cooling water or cold water outlet temperature, actually it's not TI4, it is actually TI5, okay, which is the one right after the heat exchanger right here. This is the one we're talking about here, guys. We'll see that the cooling water temperature will definitely increase, and as you can see right now, it shows a value. Okay, so every interval here is an increment by 2 degrees Celsius. So 42, 44, 46, 47 degrees Celsius. Okay, and the cooling water flow rate is around approximately 100 liters per hour. Okay. Okay, guys. So what we are going to do right now is that I will change the set point to from 25 to 20%. And as you can see right now, guys, let's have a look at the trend and how the direct action causes the output signal to increase. Now, the moment I changed the set point to 20%, the controller started to calculate the error, okay? And the error is basically the process value, which is in yellow, and the set point in red. So 25 minus 20, that is plus 5, okay? So we have a positive error, and since the control direction is direct, since we have a positive error, we expect the output signal to increase, and that's what is shown right here, guys. Okay, the moment I reduce the set point to 20, I have now a positive error, and the control direction is direct, so the output signal will increase. And it is very simple to understand, guys, because now I want the outlet temperature to be at a less value. Okay, how can I do that? The only way to do that during normal operation is by increasing the cooling water flow rate through the exchanger. Okay, I have to increase the cooling water flow rate through the exchanger in order to absorb as much heat as possible, and that will lead to a reduction in the hot water outlet temperature from here. And in order to do that, what we can do from the control system is that we have to open the automatic control valve, and as we all know, opening the automatic control valve is done by increasing the output signal. Okay. Now, this process, or and it is expected that the stabilizing the system and reaching the new steady state set point will take a while, guys, because as I said before, once we change the set point, everything inside the system will probably change. Okay, you're talking about all the temperatures inside the system, and especially the cooling water temperature, because once you increase cooling water flow rates, the outlet temperature will increase. Okay, this means that the cooling water will return to the tank, and the cold water supply to the tank, guys, is already at its maximum capacity. Okay, I cannot increase the cooling water through that valve any further, okay, because it's already at the maximum. So that will definitely cause the cooling water returning to the exchanger, or the cooling water temperature returning to the exchanger H1 to increase as well. Okay, so that explains why, as I said, controlling this experiment and waiting for the process to stabilize will take much longer time compared to the previous experiments, like the pressure inside the tank, or the water level, or even the water flow rates. Okay, so yeah, guys, it will take very long time actually for the system to stabilize. And what we need to do next, guys, is that once we reach the new steady state operating point, we will record the values again. The process value is supposed to be 20%. We will take the controller output signal. We will take the hot water inlet temperature again through this gauge right here. Okay, and after that we have the hot water outlet temperature through that gauge again. This is the outlet temperature. Okay, and then we have the cold water, or the cooling water inlet temperature, which is reported by this gauge right here. Okay, and then the cooling water outlet temperature from here, and then the cooling water flow rate using the or from the magnetic flow meter. Okay, now for the comparison, guys, between, or an essential part of this experiment, as I said before, is that since both the thermocouple and the thermometer and the gauge are at the same location, we expect them to give us the same value. Okay, so in order to compare the measured values by both of them, we need first, or we have first to convert the process value in percentage, okay, to degrees Celsius. Okay, because as you can see here, the gauge shows the temperature in degrees Celsius, and just like the last experiment, the pressure control, we need to know first the range of the thermocouple. Okay, so it's from 0 to 200 degrees Celsius, and in order to convert the percentage as a process value to degrees Celsius, we will apply this equation. Okay, so we need to know the maximum and the minimum of the sensor. We multiply that by the PV in percentage, and then the minimum of the sensor. Okay, so it was actually slightly higher than 0.25, but if we assume that we have a value of 0.25, then we will apply this equation, 200 minus 0, that is 200, multiplied by 0.25 plus 0, that makes it 50 degrees Celsius. And as far as I remember, the recorded value for the thermometer was probably around 52 degrees Celsius. Okay. So we have a slight difference between the two values, okay, during the experiment, and it is not, or some of you guys will initially say that it is an accuracy issue in one of the sensors. That is probably one cause, but there is also another major cause, guys, is that the thermometer has a much slower response. Okay. It has a much slower response to the changes in temperature. That's why what we are supposed to do, guys, is that we have to wait for a long time for the process to stabilize in order to get the most accurate value reported by the thermometer or gauge. The thermocouple on the other side, guys, is usually very accurate, and it has much faster response to the changes in water temperature. Okay. فالإشكالية هنا يا إخوان إنه فعلا number one we have an accuracy issue in the thermometer, and number two we should have waited for much longer time. But you know, guys, for a fact that waiting for every set point for like 15 minutes is almost impossible in order to get the most accurate values. Okay, so in the possible sources of error, guys, we have to mention this, is that number one, it is the accuracy of the sensor, or the accuracy of the temperature gauge or thermometer, and the slower response, guys, and we should have waited for much longer time in order to get the most accurate values. Okay, and we can do the same thing with the other set points, guys, okay, with the 25% and the 20%, but as I said, it would take probably 2 hours just to run the experiment, not to mention that the startup and shutdown procedure will take an extra 30 minutes, so that makes this video with a total duration of around 3 hours, which is very boring to watch, I know that. Okay, so as you can see, we have been discussing many things on the board. We returned back again to the process, and as you can see right now that the controller output signal has already reached the saturation point. It is now 100%, which means that the valve is fully open, guys. Okay, the valve is fully open, and there is nothing that the automatic controller can do about it, unless if I intervene here. Okay, what I can do here is that I can increase pump speed. Okay, why do I have to do that? Because basically, guys, if I increase pump speed, that will cause the cooling water flow rate to the exchanger to increase, and that will probably lead to a reduction in the hot water outlet temperature. Okay? And it's taken a very long time, but hopefully, inshallah, I will manage to redo the experiment again and try to achieve the results that we are looking for. Thank you very much, guys. I know that this experiment looks quite complicated compared to the previous ones, but hopefully, inshallah, once you read the description and watch the two videos, the one that I have already posted on Blackboard for the theory side of this experiment, and this one as well, it will be, inshallah, much easier for you. Now, for the second objective, which is basically the identifying the potential disturbances in the system and examining the automatic control response under normal and abnormal conditions. We will discuss that, inshallah, in the class. Thank you very much, guys, and hopefully we'll see you, inshallah, very soon.